Remember that I do upload these lectures, so if you happen to miss them, you can catch them later online. Today, we are spending a day talking about data modeling, and then on Thursday, we'll actually start into using an SQL database. So before we do that, it kind of helps to know what elements go into a database so you kind of know what you're dealing with. So basically, my definition of a data model is going to differ a little bit from the books. You want to use my definition. Okay, so to me, a data model is the following. It's a high-level description of the following things. One, a data's entities. So for any database, you are generally modeling some set of entities. So if it was here at UT, you have students, professors, staff, courses, you have buildings, you have accounts receivable for the university. So those are entities that would be associated with the University of Tennessee. If you're talking about the property management example we'll be using throughout this semester, your entities might be clients, property owners, the properties they own, the branches of your real estate offices, your staff, those would be your entities. So in general, your entities are going to be physical. They can be either physical or virtual. So a good example of a virtual one in the university would be courses. They don't really have a physical manifestation, but they're still there. If this was some kind of game like the, say, Warcraft, then your characters would be entities, even though they're virtual rather than physical. So then the second thing, so that's the very first thing you do when you're setting up a database is you identify the specific entities, okay? And the next thing that you typically do is you identify the entity's attributes. Okay, so for a staff member, that might be their first and last name, might be their position, their salary, perhaps their gender, perhaps their date of birth. So the various attributes that are associated with the entity. So that's kind of your first step right there. So I'll call this kind of like step one. Then the next two steps are identifying the relationships among the entities. So relationships so it's the way in which your entities interact. And we'll talk more about, actually we can talk more about it now. So you can have different, there's basically three types of relationships that we care about. So there are what we call one-to-one relationships. Okay, so an example of a one-one relationship is a staff member might belong to only one branch. Okay, so if we're talking about our property home management thing, we would say that one or a staff member belongs to one branch. Okay, The opposite side of that is what we call a many-to-one relationship. So a branch may employ many staff. Okay, and typically, instead of saying it that way, we would say one or more staff. So that's kind of a many-to-one, because you can have, a branch can have many staff. We say a staff member is one-to-one because a staff member, that side of the relationship is one-to-one because it can belong to only one branch. And then we have many-to-many relationships, which we typically denote that way. So that's a many-to-one. And that could be something like, let's see, a newspaper may list multiple properties for us, and a property may be listed in multiple newspapers. Okay, so each side of it can have multiple occurrences of that entity on it. And these relationships are typically going to naturally define the types of queries that we write. So for example, we may want to know which staff are associated with the branch on 1678 Cardiff Road. Or we may want to know which newspapers are advertising this particular property. So these relationships tend to be the ones that are going to naturally determine the types of queries that we want to write. They also are going to inform our fourth thing, which is our integrity constraints. Okay, and they can be a constraint on either a property or a relationship. Okay, so they can constrain actually I'm going to say an attribute because I don't want to confuse it with our properties that we are managing. So can constrain either an attribute or a relationship. So an example of a attribute constraint would be no employee, so we'll say attribute. Example might be no employee makes more than 100,000. Whereas an example constraint on a relationship might be that no realtor manages more than 30 properties. So no realtor manages more than 30 properties. Okay, so the difference is, in the first case with the attribute, salary is going to be an attribute of an employee. So when we say no employee makes more than 100K, we're putting a constraint on a specific attribute from the employee entity. But the second one, what we're doing is expressing a constraint on the relationship between two entities. So each property is probably going to have an attribute which lists the realtor that manages that property. And what we're saying is that if you sum up those properties that you'll never find any person's name on more than 30 properties. So we call that an example of a constraint on a relationship. And these are more complicated because you can't just typically scan through the records for a particular entity and make a yes or no decision. It involves additional work. In this case, you would have to count for each property, or for each realtor, you'd have to go through and count the number of properties that they manage. So the relationship constraints tend to be more complicated to compute and enforce. So these are the four things that make up a data model. So you start and you come up with the data entities and the attributes for the entities, and then you come up with the relationships amongst the entities and the constraints on them. Okay? So essentially, that's your job when you are creating your initial high-level data model. And you probably would get this information by interviewing. If you came in as a consultant, you would interview the employees to try to glean information about the entities. You'd use your eyes and ears. I mean, buildings are obvious things that are entities. Employees are obvious things that are entities. You'd probably take a close look at the forms. So I guess I should quickly say, how do you obtain this information? And the two biggest ways are going to be employee interviews and the second big way is going to be forms. So the various forms that are used in the organization typically are going to give you a lot of information about different entities. So leases in a property management company, or add drop forms in a university are things that are important. Obviously, entrance forms, like when you apply, those things. So those are the two biggest sources of information. We won't worry about that in this course. In this course, you'll be presented with a relatively detailed description of the problem, and that would have been the information presumably gleaned from forms and interviews. So, but in the real world, you'd have to go out, hone your interview techniques, and do this yourself. Okay, so once you have your data model, you want to typically map that data model to a database. And there are, remember, the DDL, the DML, and you'll remember that we said there were constraints on the data. So the mapping involves the DDL and constraints on the data. The data manipulation language is something the user uses, but the data model you typically are going to describe using the DDL, the data description language, and then the constraints on the data actually are something you also typically enforce using the DDL. Okay, so we then have, once you have your database, which in this course is going to be a relational database, there are, as I said, other kinds of databases out there. There's object-oriented databases. There are hierarchical, what are called hierarchical databases, or what are called network databases. They typically aren't used anymore. Typically, you'd either have a relational database or an object-oriented database. Like I said, we'll use the relational model. So you start with your physical implementation. Okay, that's where you have the files. So that's the first layer. Then above that, you have your internal view. And that is what is expressed by the DDL. Then you have your conceptual view. And that's the data model. And finally, you have a bunch of conceptual view or views that the user sees. In order to view the information. So we typically talk about different roles for the database. So the user is looking at the different views. So for example, a manager is going to have one view where they can see perhaps for their branch who's making what, so salaries plus their employees' birth dates, gender, all that information that might be considered somewhat confidential. But the manager view might only be for the branch. You might have the CEO view. The CEO view can see information for any branch. Then you might have the realtor view, and the realtor can see information about the properties they manage and maybe about clients, but they can't see information about other staff members. So here we have three different views. The CEO's view, which is an expansive view of the entire database. The manager's view of a branch, so they have a narrower view, but they still get to see much of the details associated with their branch. And then you have the employee view, which is the most, or realtor view, the most narrow, which is a view of their clients and the properties. You might have a fourth view, which might be from the leasing department. Okay, so someone, an accounting view, and they have a somewhat different view of the data. So the different views are customized for each of your different users, and they're meant to give them enough information to do their job, but not more information than they need. Okay, so call these roles over here. So then we have the DB modeler right there who's developing the data model. Then the person who does the DDL is typically called the database administrator. And what does the physical implementation is the vendor. So that's typically people like Oracle or Microsoft. Okay. So we won't get down to the physical implementation. That's actually the interesting place where all the research goes on, but is beyond the scope of this course. If you were doing a PhD in databases, generally that's where you would be doing your dissertation. It would be down there with the physical implementation. The internal view is what many of you would actually be maintaining. That's where, well, the biggest money actually is for those who can do the physical implementation, because that's the most tricky, but there's only a handful of individuals in the world who do that. But they're paid a lot of money because it's pretty complicated stuff. Then internal view, database administrator, that's kind of the IT level. And they're constantly having to update the DDL based on tweaks that perhaps are made to the data model. Okay, and they'll also be tuning the physical implementation to try to get the most possible speed out of the physical implementation. So the database administrator is a bit like the mechanic. They're not the producer of the car, but they're certainly sitting there fine-tuning the car. Okay? Then there's the database modeler, and that's what many of you will get to when you become like a project leader. So That's something that requires a good deal of experience. It's a well-paid job as well. Not something you typically do straight out of school. It would require several years of experience before you would get into the role of a database modeler. But that involves, as I said, going out and interviewing people, looking at forms, figuring out the relationships between the different entities, coming up with a detailed enough description that it can be handed to the database administrator for implementation. Okay, and finally, as I said, you have the user. These people are typically non-programmers. They may be programmers as well, depending on the application. But in a lot of cases, you have people like realtors who are just trying to pull up information from the database, and they don't have any programming experience. They're simply trained in how to write a query. And so questions about that? Okay. Oh, go ahead. Mm-hmm.
When you say, how's the information actually stored? Is it at its core, is it just binary numbers stored in?
Yes, good. So the question is, how is it stored finally in its ultimate form? Usually it's binary encoded data. Okay, so they're going for the most compact form they can get. So in your labs, everything is pretty much stored textually, right? Strings are stored textually, numbers are stored textually. They wouldn't do that in a actual thing. The text would still be stored using ASCII encryption, or ASCII encoding, but the numbers would be stored in bits rather than as text, typically. Yes. So yes, I'm not. The problem is databases aren't specifically my research area, so I know that you can do compression, but I'm not the right person to ask about it.
It's really helpful if all your records are similarly sized.
Yes. So a good point is,
linked records, oftentimes you'll partition those off into something else, so the table is actually stored as two separate things, one of which is uniform length, which makes lookups really easy, and another part that actually
is variable length blobs. Yes, so that's a good point. If you start compressing, you no longer have fixed length records, and that tends to hurt your performance. So there's that trade-off. Okay, other questions? Okay, so you have, let's say you've identified your entities, you've identified your attributes, you've identified your relationships, and you've identified your constraints. There's still a few other key things that need to be done when you are setting up your database. So the first thing is you need to identify keys. So I'll call it drilling down. So I'll call it additional things. Wow, something is happening with this pen. Just a second. Sometimes you have to recalibrate the pen. See if that works. Okay. So additional things that, wow, that's not working. Okay, take a moment. Okay, I can talk over you. I have a big voice. That I've been told actually that I had a teaching evaluation once that said Dr. van der Zanden has a very loud voice. This works both ways. Sitting in the back, I can hear him clearly at all times. However, also sitting in the back when I need to catch up on my sleep, I find it impossible to do so. So that is at least, my wife's always having to go this to me to tell me to pipe down. So at least when I'm lecturing in a big class like that, the big voice comes into for an advantage. Okay, so data modeling. Oh, come on. There we go. Data modeling, more stuff. Okay, so this is after you've done those first 4 steps that I talked about, where you identify the entities, the attributes, the relationships, and the constraints. So after that, you still, once you've identified the entities, you need to identify keys. Okay, and keys are fields or sets of attributes that uniquely identify a entity, instance of an entity. So an attribute or set of attributes that uniquely identify. Okay, so it's a little shaky, but oftentimes we consider a person's name, full name, last name, first name, middle name to be a key. So that's 3 attributes, first, middle, and last name. A zip code at one time, I don't think it's so true anymore, but at one time a zip code was supposed to uniquely identify a post office. Okay, a social security number uniquely identifies an individual. An employee ID uniquely identifies an individual. Okay, a street address combined with a zip code might or might not uniquely identify a property. So you see something that is happening here, which is you try to find what we call natural keys to uniquely identify an entity, but it gets fuzzy, right? We all can think of probably people that have the same first and last names. John Smith is certainly going to be one. And even if we go with a middle name, there's still the chance that there's duplication. Okay, with property, you would generally think a street address combined with a zip code is going to be enough, but you might have 2 cities in the same zip code. Main Street, okay, is a very common street, so you might have 323 Main Street and Farragut and 323 Main Street just outside Farragut, like in Hardin Valley. They might be the same zip code, and it's not uniquely identified. Now, if you add to that the city and the state, you probably get a unique one. But you see how squishy it is? You're never quite sure. It's close. So I make a distinction between what I call a natural key and an artificial key. So a natural key is an attribute that we create naturally. I guess it's I don't want a recursive definition. So an attribute that we how did I define it? Okay, I'll call it innate. So an attribute that we create which is innate. So your name is kind of an innate attribute. Your gender is kind of an innate attribute. Give me 1 second, okay. Give me 1 second, okay. So because it's often difficult to ensure that a natural key is unique, or because they may be verbose, or because in order to get uniqueness you may need a large set of attributes, we often create artificial keys that uniquely identify an entity. Okay, so those would be attributes that we create specifically to identify an entity. So those are things like social security number, personnel number, branch number, lease number, contract number. Okay? Those are things that are compact, typically numeric, so they can be represented typically in a 8-byte field, and they are guaranteed to be unique. Just like I got several ones, so you were first.
I was going to say, person's name is apparently not necessarily unique. It's possible to have two people with the same name.
Yes, that's what I was saying. That's the squishiness with natural keys, is that even when they're close to unique, it may not quite be unique.
Well, on the other hand, a SHA-256 hash for a person's fingerprint would be unique, although it probably wouldn't be very useful because you couldn't get the same thing twice.
Right. Now, if you took, right, so the thing is you want to be able to also generate it with minimum computational effort. So,
yeah, I know.
Yes. So, but you're right. Actually, you can do certainly retinal scans and all those other things will try to do uniqueness as well. But we're kind of just concerned here with nice, unique, compact things. So we use artificial keys. Yes.
So why is the name a natural key instead of an artificial key?
Because I know what you're saying. We kind of give people a name to identify them. But I guess I kind of think of at birth you're given your name. And so it's kind of, you probably think of your name as uniquely you. You kind of have a personal, when you hear your name, you have a personal rapport with it. Whereas if I told you your social security number, it probably doesn't have quite the same warm, fuzzy feeling associated with it. That was given to you by the government too. But you're right, a name is, but that's why I say it's innate. It's something that we consider very fundamentally part of us. Okay. Other questions? And I'm not going to test you on something like that. It's important that you kind of just have this idea that the reason we create artificial keys is because it's very hard to ensure that a natural key is going to be unique, at least if it's compact. In general, if you get enough attributes, like with a property address, you can probably eventually, with say the property street address plus zip code plus city plus state, with those 4 attributes, you probably have guaranteed uniqueness, but that's such a big set of attributes, it's kind of unwieldy. So the idea here is simply we typically add an additional attribute to uniquely identify an entity to keep it compact. And also, as we'll see, while we try to eliminate redundant data, like we don't want to keep your salary multiple times in the database. We don't want to keep your eye color multiple times in the database. But there's one thing we can't avoid storing multiple times in a database, and that is the key. Okay, so the reason we can't avoid doing that is because
Today is 1325 and Betty's
it's okay.
Knoxville Dermatology 123.
Okay, so we call this first kind of key a primary key because that uniquely identifies an entity. We have a second kind of key that's called a foreign key. Okay, and it is used as kind of a pointer to allow us to get information about another entity. So for example, I said that a property, one of the attributes for a property might be a realtor number. So the realtor number is actually the number of a realtor that we can use to index into the realtor file and find out information about that realtor. So instead of repeating all the information about the realtor in the property record, so instead of saying the realtor's name is Brad Vander Zanden at 1678 Cardiff Road, instead we just say the person who manages this property, their number is 386. And then if we want more information about realtor 386, we can look up realtor 386 in the realtor file and find out, oh, realtor 386 is Brad Vander Zanden, who works out of the branch at 1678 Cardiff Road. So the realtor number is like a pointer into another file. Okay, and we call that a foreign key. So a foreign key is an attribute, which I'm going to abbreviate ATTR so I don't have to keep writing it out as attribute, which is a primary key for another entity. Whoops, there's no. So a foreign key, it serves as a pointer to that other entity. And it represents a relationship between the two entities. So once you've identified your relationships, you typically are going to be adding attributes, which are foreign keys, so that you can model these relationships. Okay, so you can't avoid redundantly storing keys. Like the realtor number is going to be something that is a redundant piece of information. So databases seek to minimize the amount of redundant information, but they can't eliminate it completely. And because keys represent redundant information, we want to store a key as compactly as possible because it's going to be duplicated in multiple places in our database. And therefore, we don't want to waste a lot of storage on them. So that's another reason that we tend to come up with artificial keys that we can compactly represent. Okay. So then let's go back to the final thing I want to talk about today. Oh, except I blew it away. Okay. So I'm going to come back to our previous model of things. So we had these three layers. We had four layers: physical implementation, internal view, which was the DDL, we had the conceptual view, which was the data model, and we have the user views. Okay, so a database gives us independence among these different levels that is very nice. So first of all, there is this independence between the physical implementation and the internal view. So we call this physical independence. And it means that we can change that if we change the physical implementation, we don't have to change the software that's on top of it, like the queries. So we can change the physical implementation without, which I'm going to abbreviate as WO, without changing the programs written on top of it. I'll specifically say the query programs. Okay, and then the second thing we have is this idea of logical independence, which is that if you change something in the database model and it's not of any concern to a view, then that user is unaware of it. So let's say that I add an additional field to the staff. So perhaps it is, for some reason, we need to know the number of dependents. So we add a field called number of dependents. So there's two people who might care. Just a second, I'll get to you in a moment. There's two people who might care, the branch manager and the CEO. But the realtors and the accountant shouldn't care about the number of dependents that each staff member has. So while the CEO's view will change and the branch manager's view will change, the realtor's view and the accountant's view will not change. So we call that logical independence. And the nice thing about that is that views are often cached, so that if the person asks a question and that query's already been run, it can simply be taken from memory without having to run it physically against the database. So logical independence means that we don't have to throw away cache results every time we make some modification to the underlying data model. Okay, so it's logical independence means views should not change, or when entities change, unless the view is directly affected. Okay. So those are two big advantages that databases give us. Okay, so next time, things get more interesting from here, to be honest. If you thought today was a little slow, I feel like today is a little slow, but it's necessary in order to kind of give you a high-level overview of where we're going. So starting Thursday, we are looking at first the user view. Okay, and we are talking about how to write queries, how to change queries, or, well, basically how to write queries and update information in the database. So that's the first thing we do. Then we kind of drop down to the internal view, and that's where we get to the theory. So after we talk about the user view and the direct manipulation language. Then we drop down and talk a bit more about the theory and the DDL. So that's where we talk more specifically about here's the relational model and how it's organized. Then we spend a couple weeks talking more about design, which is the creating the database model. And that's where you'll hear terms like normalization and entity relationship models. So that's what we talk about third. And then the last thing we talk about is how these things are stored. And that's where we get into things like indices, B+ trees, and extendable hashing. So these are all have to do with how files are physically stored on the disk. So those are kind of the four big areas that we talk about, each of them getting about 2 weeks except for number 4. Number 4 gets about 1 week. And that's, so next time we get into the queries, we'll spend about 2 weeks, and probably, we'll see, sometimes during the user part I have you write queries and the like, so try to bring your laptops with you to class for the next couple weeks, okay? Because I might want you logging into the Hydra machines and trying to write some queries of your own. So I will see you on Thursday. You don't have to worry about homework for a couple weeks, so don't worry about that. But remember, you do have your Blackboard quizzes. Do that by Thursday.